Okay, let's talk about complex numbers, which form section 1 of Fraley. I'll assume that you've had some exposure to it before, so I'll go a little bit quickly. But if you haven't, please look up some YouTube videos on complex numbers. Okay, so the complex numbers as a set, well, you can think of them as written as a plus bi, symbols where this I here is just a symbol for now, and a and b are elements of the set of real numbers. More formally, you can think of the complex numbers as the underlying set being R2, in other words, just pairs, ordered pairs of real numbers. And okay, so the examples are 2 plus 3i, root 2 minus 1 half I, and so forth. And what we're going to say or show or establish is that the complex numbers can be added, multiplied, subtracted, and divided, just like you do for rational numbers. So they form what's called a ring, and in fact a field. Those are terms we'll encounter much later in the course. But the addition is very simple. You just, if you want to add a plus bi and c plus di, you add the real parts a and c, and then add what's called the imaginary parts b and d. Those are the parts that are the coefficients of I. They become the new coefficients of I. And okay, so here's how addition is defined. Multiplication is defined basically like the FOIL rule. And the key point is that I squared becomes -1. And so when you FOIL out, for example, bi times di, you get bdi squared. I squared we're setting to -1. And so then the real part of this product becomes, well, the AC term, and then the negative BD term from here. That's the real part. And then the imaginary part is coming from A times DI, so that's where the AD here comes from, and then BI times C, that's where the BC I come from. So this is again just a definition of multiplication. As for division, well, if I have two complex numbers, A plus BI and C plus DI, the way I define division, well, here's how to figure it out. We're going to multiply by the complex conjugate of C plus DI. In other words, C minus DI is what's called the complex conjugate of C plus DI. And then when you FOIL this all out, the point is that C plus DI times C minus DI is C squared plus D squared. So that's a real number. And then in the numerator, when you FOIL this all out, you get AC plus BD, some real number, plus some imaginary part. And so this is how division of two complex numbers is defined. Again, what we need is C squared plus D squared to be non-zero. It's only defined then. Okay, I didn't mention subtraction, but it's very similar to addition. Now, the fundamental theorem of algebra states that every polynomial with coefficients in the complex numbers has a root or a zero in the complex numbers. And this is a very difficult theorem to prove, although there is a very quick proof using complex analysis. We probably won't see a proof in this course, but okay. Now, the real numbers sit inside the complex numbers as the numbers with imaginary part 0. So if a is a real number, you can think of it as a complex number a plus 0i. Now, there's something called the norm of a complex number that measures, in a sense, the size. And so the definition of the norm of a plus bi, so the norm is written using absolute values, and by definition, it's the square root of a squared plus b squared. So for example, the norm of the complex number 2i is the square root of 2 squared, which is just 2. Another example is the norm of 1 plus I is the square root of 1 squared plus 1 squared, and so the square root of 2. And we can plot the complex numbers in the xy plane just because the underlying set of the complex numbers is R2, and so the complex number x plus yi is plotted or corresponds to the point x comma y. So for example, 1 plus I is at the point 1 comma 1, go over 1 in the x direction, up 1 in the y direction. The complex number 2i, which is 0 plus 2i, has 0 x component, and then go up 2 units to get the y component, and similarly. Sometimes this is called the Argand diagram. Next, I want to talk about Euler's formula. Well, one of his formulas, the one that says that e to the ix is equal to cosine x plus I sine x for x, any real number. Sometimes you'll see instead of x, you'll see theta. That's a little more typical. So what's the proof of this formula? Well, we have to go back to calculus. So the definition of e to the z, how to take the real number e and raise it to the zth power, is using the power series for the exponential function, namely 1 plus z squared over 2 factorial plus z cubed over 3 factorial. And this is in fact the definition for z being any complex number x plus iy. That's how e to the z is defined. So taking z to be the complex number I times a real number x, that means e to the ix is, you just substitute ix everywhere there's a z, and for example, this z cubed turns into ix cubed, which is I cubed times x cubed, and I cubed is I squared times I, and I squared is -1. So I cubed turns into -I. And what we want to do is collect the real and imaginary parts of this power series expansion. Again, this continues on forever, but I've only written the first 3 or 4 terms. So this one is here. This ix is going to be part of the imaginary part, the part that has an I, since x is real. This I squared turns into -1, and so this circled part is a real number. X squared over 2 factorial, that's a real number. This part here that I've boxed is an imaginary number. It will have some I times some real number. Okay, so collect, and this part here is circled, and so it's a real number because the I to the 4th is I squared times I squared, which is 1. So collecting the real and imaginary parts, so I've collected the real parts here. Again, these are the parts that don't have an I appearing in them. And then these are the parts that were boxed that do have an I appearing in them. This is the imaginary part. We see that the real part is, again, this is just the first 4 terms. I should have a ... here. It goes on forever. It's the power series associated to cosine of x. That's, again, some fact from calculus. And then this here is the power series for sine of x. And these power series converge for all real values of x. And so what we conclude is that e to the ix is equal to cosine x plus I sine x. That's what Euler's formula says. And then a acute consequence, a kind of a famous one, is that if you plug in x equals pi, what we get is e to the I pi is equal to cosine pi plus I sine pi. Cosine pi is -1, sine pi is 0, and so this term becomes -1, this term becomes 0, so we're just left with -1. So we get that e to the I pi is -1, moving the -1 to the other side by adding 1 to both sides, what we get is e to the I pi plus 1 equals 0. And what's cute about this is that it's an equation combining all the basic numbers in math, e, I, pi, 0, 1. I mean, it's just cute. It doesn't have a whole lot of, theoretical significance necessarily. Okay, so then let's move on to talking about polar coordinates a little bit. So remember, a complex number has a real part x and an imaginary part y, and we can plot it like so. The x coordinate is the real part, and the y coordinate is the imaginary part, again, the part that has an I in there. And then the norm of a complex number we define to be the square root of x squared plus y squared. And if you look at this right triangle here, that's the hypotenuse. Due to the Pythagorean theorem, x squared plus y squared, the hypotenuse is going to be the square root of that. And then if you remember from polar coordinates, basically x is equal to r cosine theta, where theta is the angle that the point makes with the positive x-axis. looking at this right triangle and using SOHCAHTOA, you can conclude that x divided by r is equal to cosine theta, so that's how we get this equation. And similarly, sine theta is opposite over hypotenuse, and rewriting that equation gives that y is equal to r sine theta. And so I'm going to claim that, well, a couple things. So first of all, what we see is that the norm of z, a complex number z, is equal to the r. That we kind of see from this picture here. And that the complex number z, we can write it in terms of the variables of polar coordinates as the absolute value of z, which is, I should have written here, I mean, I have written here r, but I should have written here r. So r e to the I theta. And that's what I do to get that down here. Okay, so why is this the case? Well, we know that the complex number z is x plus iy. It's got a real part and an imaginary part. And the x is equal to r cosine theta. So now we're switching from the x and y coordinates to the r and theta coordinates of polar coordinates. Similarly, the y is r sine theta. Let's factor out the r here and the r here to get this. And then we know from the Euler formula that we just proved is that e to the I theta is cosine theta plus I sine theta. Okay, so we get that z is equal to r e to the I theta. This is a very useful formulation, as we'll see. So here's an example. We've got z, this complex number 1 minus I, and the question is simply write it in the form r e to the I theta. For some reason, I kept writing the absolute value of z. I wish I'd written r e to the I theta here, basically in polar coordinates. Okay, so the solution is the norm of z is the square root of 1 squared plus negative 1 squared, and that's the square root of 2. And then we have to find out what the theta is, and that's depends on the position in which quadrant. So we've got 1 minus I. So we go over 1, down negative 1. So 1 minus I corresponds to the point 1 comma negative 1. And theta is usually measured from the positive x-axis. Sometimes, so you could measure this way, in which case theta would be negative, again from the positive x-axis. And when you do that, you get that tangent of theta is y over x. And so so I'm using the theta down here. The y is equal to negative 1, the x is equal to 1. So theta becomes arctangent of negative 1. And if you ask what's that in the calculator, you'll get negative pi over 4. And so that's, the negative comes from you're going in basically the clockwise direction. And then, so what we see is one answer is 1 minus I is equal to root 2 times e to the negative pi I over 4. An equivalent answer, or correct answer as well, would have been if you take this exponent here and add 2 pi I to it, or any multiple of 2 pi I. And the reason is that e to the 2 pi I is equal to 1, once again due to the Euler's formula. I should have written that earlier, but I just mentioned it, or did that right here. E to the 2 pi I, what is that equal to? Well, Euler's formula says take the 2 pi and plug it into cosine, plug it into sine, and put an I on the sine bit. Cosine of 2 pi is 1, sine of 2 pi is 0, because 2 pi corresponds to 360 degrees. And so if you look at your unit circle, your do a full rotation of 360 degrees, which from the positive x-axis, which means you're back on the unit circle at the point 1 comma 0. That's how you get 1 here and 0 here. So e to the 2 pi I is equal to 1. Okay, let me go up here to de Moivre's formula, and this is a simple consequence of something we've seen previously, that z is equal to r e to the I theta, or absolute value of z times e to the I theta. And de Moivre's formula says is just simply taking this equation and raising it to the nth power. And so the absolute value of z, or the norm of z, is raised to the nth power. And when you raise e to the I theta to the nth power, you get e to the I n theta. And sometimes the way this is written is r to the n cosine n theta, because e to the I times n theta is, by Euler's formula, cosine n theta plus I sine n theta. So de Moivre's formula is generally this line here. Z to the n is r to the n cosine n theta plus I sine n theta. So let's see how we can use this. Well, here's a simple example. Compute 1 minus I to the 2019 power. And the trick is to use the polar coordinate expression that we found for 1 minus I. This was the previous example we did. We found that 1 minus I is root 2 times e to some exponent. Okay, and so just raise that to the 2019th power. That's essentially what we're doing here. And so, okay, root 2 to the 2019th is some big number, and then e to the negative pi over 4 times 2019 is this. But what's key is that this number down here, or out here, can be simplified, and I've done that below. So what we have here is that 2019 is, well, 2016 plus 3, and 2016 is a multiple of 4, namely 504 times 4. Okay, and then we've got this 3 left over, so we've got this, and e to negative pi times an even number is 1. That's this idea here. E to the 2 pi I equals 1, and so this e to some even number is equal to 1, and then we're just left with this thing here. And then when we look on the unit circle, where does 3 pi I over 4 land? That lands out here at this point, negative 1 over root 2 minus I over root 2. I went over this a little bit fast, so I apologize if it's not entirely clear. If you don't understand this last part, it's my fault, and I'll do an example in the next video.